The connection to be symmetric, but it doesn't have to be. So precisely today's seminar will be devoted to the calculations of evolution of time-like congruences. And here just the summary. Yeah, first I will talk a little bit about the step by step to derive evolution equation for expansion, shear and vorticity. These equations are called Raychaudhuri equations. They are a bit technical in a sense that it's a bit more mathematical, but it has huge physical applications. And this Raychaudhuri equations is one of the pillars of this, the famous Penrose singularity theorem. Yeah, so we know that in GR, a particle can be moved in a geodesic and we can determine them from geodesic equations. But if we have a bunch of closely separated curves and propagating in a space time, then how can we determine how they are propagating? So this can be determined by Raychaudhuri equations, and one of the great features of these equations are that they are purely geometrical in nature. They do not assume any theory a priori. So basically we can have these generalized equations, we can incorporate with any theory of gravity in these equations and try to investigate how the bunch of curves are moving in the space time. And when we decide the theory we want to test, then we basically will have energy momentum tensor related with the Ricci defined in that space time. So we will see how it can be done. And these equations with torsion basically can be used to study the space time with torsion. And nowadays like people are very much working in this field to test many theories of gravity which departs from GR. Basically if there is torsion, as I said, we will see in a minute in a more detailed way what does it mean by torsion. And these equations can be used to examine the prediction that the singularity could be avoided in the presence of torsion. In fact, there could be a bounce. And also as I said, so by gravitational waves, there is a big community nowadays testing the theories of gravity from gravitational wave signals and put a constraint on the theory. So these calculations even can be used in a more applied way to test the theories of gravity with torsion. And in a more precise way, we can say that in a theory with of gravity with torsion, in which case torsion can be non-propagating one, such as Einstein-Cartan theory, or there can be a dynamical degrees of freedom related to torsion. So the definitions here, we see that the covariant derivative can be written as this nabla alpha x beta, where x beta is a 4 vector, and this C beta alpha sigma is a rank 3 tensor, mixed one in nature. So it's a generic connection, and we have only constraint here that the metric should not be changed, it should be parallelly propagated in the space time. So we are assuming that the zero non-metricity, and we define the torsion tensor to be the antisymmetric part of the generic tensor C. So you see here by construction this S, which is called the torsion tensor, is antisymmetric in its first two indices. Sorry. Yeah. So basically in GR, this connection, this generic connection is the Levi-Civita one. Yeah, so as I said, so it is torsion tensor is antisymmetric in its first two indices, and this generic connection can be written as the sum of Levi-Civita connection plus some contortion tensor, where this contortion tensor is related to torsion tensor, as you can see here. So in GR we have a connection, that's the Levi-Civita one, that is a symmetric connection. So we excluded the antisymmetric part, and when we include the antisymmetric part and write in a more generic way, then we have this connection, and with this connection we depart from GR. Yeah, so here is the expression for Lie derivative of a vector v mu along another vector u mu, let's say, which takes the form this. So we know that this is the expression for Lie derivative. So if we substitute this partial derivative with the full covariant derivative, then we arrive to this expression. So here this nabla alpha is the covariant derivative with respect to full connection, where we have Levi-Civita part and also contortion part. So if we just substitute this with full covariant derivative, then we have some term here that is really related to the torsion tensor. And the other definition is that we can define the Riemann tensor with respect to the full connection C in a very similar way if we would have described it with Levi-Civita connection. Okay, the next property is that we know that the commutator of covariant derivative in GR if we apply this operator on a vector, then we get the Riemann tensor, one indices contracted with the vector. So here is the connection, here is the correction, that we have some contribution from torsion. So it is definitely not the same as if we are in GR, and we can also write some generalized Ricci tensor if we contract this indices middle one with the fourth one. So we can write this expression with respect to the generic connection, and Ricci scalar can be defined as usual if we contract the metric with the Ricci tensor. Yeah. So when a bunch of curves propagates in a space-time, let's define two vectors which can help us to determine how they are propagating in a space-time. So basically the separation vector and the vector that is tangent along the direction of flow. So here we have a bunch of curves. This let's say gamma s lambda, where s when we change from one curve to another. So s is changing along this direction, let's say when we are changing from one curve to another, and this lambda is parameterizing the curve along the way. So this is lambda is the parameter that changes along the curve, and s is when we change from one curve to another. So we can define a separation vector, this alpha, as the partial derivative of x alpha with respect to this s parameter, and we can also define a tangent vector as u alpha when we calculate the partial differentiation with respect to lambda. So here we know that this is the definitions of the Lie derivative. So here what we are calculating? We are calculating that the Lie derivative of the tangent vector along the separation vector. So we are calculating how the tangent vector is changing along the separation vector and maybe the vice versa. So if we incorporate the definitions of u beta and this xi beta, then we have basically this expression, and if we calculate all the steps, then we get it as 0. And if we then calculate by incorporating our earlier calculated expressions, so this is basically 0. So if we just manipulate little bit, then we see that the separation vector is changing in a way and can be completely determined by the characteristic of the tensor B. So here we can see that B is basically telling us how this separation vector moves along the flow as it flows. So if we know the properties of B, we can surely determine how those curves are moving along the space-time. And here is the definitions of B, and we can clearly see that this is the contribution coming from torsion, and this is the definition if there is no torsion at all. So when a bunch of curves moving in the space-time, then what could happen? So it could expand, as you can see from here. So it is basically expanding while it is moving, and there can be shear. So basically it can be stretched or squeezed, or there can be rotation. And so these can be three most generalized situations what can happen during the propagation of those curves. Okay, so now we define the projection operator. So projection operator H alpha beta is defined as G alpha beta minus sigma U alpha U beta, where U is the tangent along the direction of flow, and this sigma can be -1 or +1 depending on whether those congruences are time-like or space-like. So in a more general setting, when we have torsion, this B tensor can have non-zero tangential component along the direction of flow. Basically, what I meant that this is tangent to the hypersurface orthogonal to the flow. So we will see in a minute how to get these components for time-like congruences. So we have a perpendicular part and a parallel part. So we can project this B along the plane perpendicular to the direction of flow by using this relation, and if we using this above relation, we can simply subtract the perpendicular part and get the parallel one. And we can write in a more general setting that this B perpendicular alpha beta can be written as the combinations of expansion, shear tensor, and also this vorticity or twist tensor, let's say. So this theta is the trace of this metric, as you can see here, and this sigma shear tensor is basically traced out part from the symmetric part of this this tensor, and this vorticity tensor is completely antisymmetric part of the perpendicular component of B. So this is the most general decomposition of the tensor B. So we have here expansion, shear and vorticity, as we have seen a minute ago in that picture. So now what we have to define? We have to define a projection operator for time-like congruences. So here, if we use this operator, then we can project the tensor B onto the hypersurface orthogonal to the direction of flow, and we have this relation, so which has to satisfy. So this operator is itself perpendicular along the perpendicular to the direction of flow. So as you can see here, if we contract this with V alpha, where V alpha is the tangent to the time-like curve, so that is 0, and we have this relation here, and the trace of this metric is the n minus 1, so where n is the dimension of the space time. So we will use this and then calculate how the expansion equation looks like. So now we have to calculate the perpendicular component of B alpha beta. So if we use the relation here, so we are basically projecting the tensor B onto the orthogonal hypersurface which is perpendicular to the direction of flow. So we use the relation of H alpha gamma as it is written here, and if we just calculate those, we are not going step by step to derive it, but just for completeness as it is here. So let's come here. So you can see here is this V sigma V beta nabla alpha V sigma. It is 0 because I will use a board for a moment. So V sigma nabla alpha V sigma, this is the expression that we have there. So we know that V sigma is -1 for time-like congruences. So we can apply this nabla alpha V sigma which is 0, and we can write it as V sigma nabla alpha V sigma plus equal to 0, and we can play with that and we can show that these two are basically identical. So we have 2 times V sigma nabla sigma V sigma equal to 0. So basically we can say that this is 0. So we have here this is equal to 0, and we know that this torsion tensor is basically antisymmetric in its first 2 indices. So, and we are contracting this, we can see here first indices rho with V rho and second indices gamma with V gamma. So when we have antisymmetricity in some indices and then we contract, so basically it means that S rho gamma beta V rho V gamma, it is 0 because we have antisymmetricity in this antisymmetric property in these first two indices. So that means that rho gamma beta is minus gamma rho beta. So we can use this antisymmetric property, and we can say that this is going to 0, and this is also 0 by using the same V sigma nabla gamma V sigma by using the same property. And also if we use the antisymmetric property of the torsion tensor, then that is also 0. So in the end we have this expression where this alpha beta is V gamma nabla gamma V beta. So that is basically we can say it is acceleration, which is 0 if we are considering the geodesic. We are not putting alpha beta to 0 here, and we will expand it for the torsion case, and we will show it later. So the parallel component of B alpha beta can be written as just subtracting from B alpha beta to the perpendicular component, and we have here this, and we can see from this expression that if there is no torsion, so this is 0 and this is also 0, because this A beta is acceleration, which is basically 0 if we are in GR. If we are not in GR in some sense, but if we are considering that we are moving along the geodesics and we are in GR more specifically, so this is 0. So B perpendicular alpha beta is 0 if we are in GR, but here it is not the case. We have some corrections because we have some extra degrees of freedom due to the presence of torsion. And now let us expand the covariant derivative. So if we expand the covariant derivative, then we have to expand the generic connection C, which we can do by writing this Lebesgue part and also contortion part. Then we are here, and we can say that this nabla tilde is the covariant derivative with respect to Lebesgue connection. So this is the expression if we open up this nabla alpha, which is defined with respect to the generic connection C, and if we expand alpha beta, then we can see here, and this part is basically pure Lebesgue part, and if we are considering the geodesic, then this should be 0 because there is no acceleration if we are flowing along the geodesic. So we have only non-zero part coming from the contribution of contortion. So we can open up those covariant derivative, generic covariant derivative, and we have this expression for perpendicular component of B, and we can also determine which is the parallel component, which is the same. So now we want to determine how this expansion changes, or in some sense how the expansion evolves when we move along the congruence. So this perpendicular component of B without torsion can be written as this expression nabla tilde alpha V beta. So this is basically theta tilde if we contract with projection operator. So basically calculating the trace of this B tilde alpha beta, and we have this expression. Now what we want to prove? We want to prove that the general expression for theta is the same even if we have torsion. So that means basically theta is a scalar. It is the trace of this tensor, and due to the presence of an extra degrees of freedom, there is torsion, but these scalars are not affected by the presence of some extra degrees of freedom which is tensorial in nature. That is worth to mention. So if we calculate the trace, then we have here this theta tilde. Theta tilde is without torsion case, and then we have some correction due to the presence of torsion here, also here, and we can use the same property that S is antisymmetric in its first two indices. So if we contract with V rho V alpha, then that is 0, and also this K contortion tensor is antisymmetric in its last two indices. So if we contract with this V sigma V beta, then that is 0. So we have expanded this K here in this parenthesis, and we can see that S is antisymmetric in its first two indices. So if they are self contracted, that is alpha alpha, then that is also 0. And if we just calculate this, then we can see that theta equal to theta tilde. So basically, even if there is torsion, the expansion scalar is not changing, at least formally. So we can say that this theta equal to theta tilde even in the presence of torsion. So now let us calculate how the expansion changes along the congruence. So that is basically capital D theta D tau, where tau is the proper time. So it can be written as this expression B mu nabla mu theta, where B mu contracted with nabla mu theta, it gives us exactly this expression by definitions. So, and as theta is scalar, so we can substitute this covariant derivative with the partial derivative, and we know that theta is already equal to theta tilde, which is the Levi-Civita part, that is GR part. So we can substitute this, and again we promote this partial derivative to the covariant derivative. So we can, and this is the definitions of d tilde theta tilde d tau. So this is the Raychaudhuri equations for expansion without torsion, and this is with torsion. So here we just substituted the expression for Raychaudhuri equation with without torsion. So we can see that even in the presence of torsion, these two equations are the same. So there is no change in the equations formally. So here these tilde quantities are calculated with respect to the Levi-Civita connections, and the other quantities are with respect to the full torsion full connections. So basically here we can say that this is the same equations as if it will be in the GR, but there is some caution. This Ricci tensor is not the same if there is torsion. So even though if it is formally the same, but it will be different when we incorporate the theories of gravity. So this is the Ricci tensor in GR, and if we have torsion, then this will be different. So formally these expressions are the same, but it is not same when there is torsion. Yeah, so now the equation we are going to calculate is the equation governing shear. So shear can be defined as the traced out symmetric part of B perpendicular alpha beta. So this is sigma tilde alpha beta, so that is with respect to the Levi-Civita connection, and here we have the expression. Here we have just substituted that H gamma gamma is n minus 1, and the general here, that is with torsion full torsion, in a torsion full case, the same expression, and if we use our previous calculations of B perpendicular alpha beta, then we get the relation with this sigma tilde alpha beta, that is with Levi-Civita connection, with respect to Levi-Civita connection, and there is some correction due to the presence of torsion. Here you can see that all these terms, this is contortion, so contortion is related to torsion, so this is because of torsion, this is torsion tensor, this is torsion tensor, here is contortion. So F alpha beta is basically arising because of the presence of torsion. So if we calculate how this shear will change along the congruence, then we calculate this expression and we substitute sigma, we open nabla mu with which can be written as this contortion part, and this is Levi-Civita part, and if we just calculate this, then we have here sigma alpha beta, where sigma alpha beta we can write as sigma tilde alpha beta, which is the contribution coming from the Levi-Civita part, and this is F alpha beta, which is completely torsion contribution. So if we expand everywhere with sigma tilde alpha beta plus F alpha beta, then we have this expression, and this one you can recognize, this one is the how sigma tilde alpha beta, that is with respect to Levi-Civita connection, changes along the congruence when there is no torsion. So this is basically this one. So that is the Raychaudhuri equations without torsion for shear, and then here we have some corrections due to the presence of torsion. So now we substitute the Raychaudhuri equations for shear in the previous equations, and here in the square bracket, inside the square bracket we have the Raychaudhuri equations for shear in a torsionless case, and here we have the corrections due to torsion, and this Ricci RT alpha beta is the projected Ricci tensor, and C alpha gamma beta rho is the usual Weil tensor. So we can see from these equations how the torsion modifies the Raychaudhuri equations for shear. And now we want to calculate how the twist or vorticity or the rotation tensor changes along the congruence. So this is the rotation tensor or let us say vorticity tensor omega alpha beta tilde without torsion, and this is the expression, that is the completely antisymmetric part of the perpendicular component of B, and the general expression of vorticity we can write it as this omega tilde alpha beta plus G alpha beta. If we expand this B antisymmetric combinations of perpendicular component of B, then we see that this G alpha beta is the contribution coming from the torsion, and this is the Levi-Civita part. And if we calculate the Raychaudhuri equation for vorticity, then basically we have some corrections due to torsion as it was earlier, which can be recognized here. So if we just follow the steps as previous, so we opened up this nabla mu with Levi-Civita part plus contortion, and here this expression V mu nabla tilde mu omega tilde alpha beta, this is basically the Raychaudhuri equation for vorticity, in the absence of torsion. So that is here, and we have the correction due to the presence of torsion. So we can say that here we have the Raychaudhuri equations for torsion, but we can write it as the Levi-Civita part plus some corrections that arises due to the presence of torsion. So we can substitute the Raychaudhuri equations without torsion for vorticity here in the square bracket, and the rest is the corrections arises due to the presence of torsion. So what we have seen today, that these Raychaudhuri equations in a space-time with torsion can be written in a way that there is Raychaudhuri equations without torsion plus terms due to the presence of torsion. So we have managed to generalize Raychaudhuri equations in a presence of torsion that can be written in this manner, and these equations will be very useful to test the theories of gravity with torsion, and also for other purposes, like that there's also people working on the focusing using the focusing theorem and all that. So in the next seminar we will see how these equations can be generalized for a null congruence in detail, and this null congruence is a bit more interesting in the sense that this is the basis for the Penrose singularity theorem, and we can see that those equations are a little bit more complicated, but it can be written in the same manner. So we have to also define the projection operator for null congruence, which is not trivial like the time-like case, because we need the help of an auxiliary vector to define the perpendicular plane to the direction of flow. So that we will see in the next seminar, and these are the references, and if you are interested you can have a look at the book by Eric Poisson, this relativist toolkits, and also there are other articles. So one is by my collaborator here, Vincenzo Vitaliano, which was published, and the other one that I have published with Professor Liberati. So that's all. Thanks for your attention.